Hello, my name is Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 9, Section 4, titled Vectors. By the end of this video, you will have reviewed recent lessons describing vectors. Discussions will include describing a vector direction, and adding vectors. We will conclude by reviewing a real-world problem that requires the use of vector addition. If you would like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video to be helpful. Thank you. Okay, Objective 1, describing vectors. A vector is any quantity with magnitude, which is the size, and direction. There are many models for a vector. You can use an arrow for a vector as shown in the velocity vector KL. You see the arrow here across the top of the KL. The magnitude corresponds to the distance from the initial point, K, to the terminal point, L. The direction corresponds to the direction in which the arrow points. You can also use an ordered pair, x, y, or the xy pair, in the coordinate plane for a vector. The magnitude and direction of the vector correspond to the distance and direction of the x, y, or the xy from the origin. Example 1. Describing a vector. Describe OL, the vector OL, as an ordered pair. Give the coordinates to the nearest tenth. So you see the picture we have here. There's a vector. It's O to L. That's the vector. You see the direction it's headed by the direction of the arrows pointing. And we see an angle, 50 degrees. We see a size of 65 units, whatever that 65 is. Okay, use the sine and cosine ratios to find the values of x and y. So cosine of 50 degrees is equal to x divided by 65. So if we look at, here's our angle 50 degrees right here. Here's the 50 degrees. Let me see if I can draw that right there. Here's the 50-degree angle right there. And we want the x, the value of x. Well, x is equal to what? Of this sine, this is the adjacent side, right? 65, x is the adjacent side. So 50, the cosine of 50 degrees is equal to x divided by 65. And when we get to the sine, we're looking for the y value. That's the distance from the x-axis vertically. Okay, and there we have the sine because we're trying to get the y value. Here's the y value. And the y is opposite the 50 degrees. So we use the sine, put y over here, and that over 65. So going back to our numbers, cosine of 50 is equal to x divided by 65. And sine of 50 is equal to y divided by 65. So when you're solving the cosine of 50, you're going to solve for x. So x is equal to 65 times the cosine of 50. X is approximately equal to 41.78119463. Okay, units, whatever those units are. As for the y value, it's the sine of 50 equals y over 65. So we move the 65 over to the sine. So we have y is equal to 65 times the sine of 50 degrees, which y is approximately equal to 49.792888. Okay, you use the calculators to actually get the sine and cosine value and then do that multiply. So, and note, L is in the fourth quadrant, right? When we look at this as our coordinate plane here, Cartesian plane. This is 1 up here, 2, 3, and 4. We're in the fourth quadrant. And in the fourth quadrant, x is positive, y is negative. So L in the fourth quadrant, so the y coordinate value is negative. So OL marked off on the coordinate plane is equal to 41.8, that's to 10th degree, 41.8, comma, negative 49.8. Okay? Okay, example 1, check your understanding. Describe the vector at the right as an ordered pair. Give the coordinates to the nearest tenth. Okay, check your understanding. So go ahead and stop the video, pause it, and try this yourself. And when you come back, we'll look at it together. Okay, now that you've had some time, you're back. So let's start off by getting the y value. Okay, the y value is equal to the sine of 65 degrees. The 65 degrees is right here. Here's the 65 degrees, right? And the sine value, if you look at it from tip to down here, this is the sine, right? It's the sine opposite. This is the side opposite. So it's opposite divided by the hypotenuse, and the hypotenuse is the vector itself, 51. So y divided by 51. Sine of 65 degrees is equal to y divided by 51. So y is equal to 51 sine of 65. All we did is solve for y here. So y then equals 51 times 0.906307. It's an approximate value when you get to it. And y is approximately equal to 46.221679 when you multiply the entire number out. Okay? So, or 46.2 to the nearest tenth. Now to get the x value, it's cosine of 65 degrees. So it's cosine of 65 is equal to x divided by 51. We solve for x at this point, and we get x is approximately equal to negative 51 times 0.4226182, which is also then, when multiplied out, gives us x is approximately equal to negative 21.553, or negative 21.6. And why is it negative? Because when you look over here, you see that our vector is in the second quadrant, right? Second quadrant. And in the second quadrant, x is negative, y is positive. So we're doing x is negative, y is positive. So coordinates to the nearest tenth are x equals negative 21.6 and y is 46.2. Okay, example 2, describing a vector direction. In many applications of vectors, you use the compass directions, north, south, east, and west, to describe the direction of a vector. So let's look at A. So this chart here shows like a compass, right? North, south, east, and west. And we have an angle, a vector at a depression angle, an angle of depression, 25 degrees. Okay. So how do we state that in terms of to name the direction of this vector? So we can say that it is 25 degrees south of east. So as you see, we're drawing down from the east, down toward the south. So we are 25 degrees south. That's south means of east, means we're below the east, right? We're south of the east. If we were north of the east, we'd be on the upper side, north of east. But this is how we've chosen. You could say also, you could have said that we're what? That we're 65 degrees east of south. You could have also said that, right? Going the opposite direction. And let's look at B. B says we have 35 degrees is our angle. And it's 35 from where? It's 35 degrees from the north, vertical, right? Because it's rolling around clockwise, away from north, out to the clockwise direction. So this thing is 35 degrees east. We're headed east of north. We're heading east of or from the north, east of north. Sketch a vector that has the direction 30 degrees west of north. Okay, let's check your understanding here. And it says, give a second description for the direction of this vector. Okay, so go ahead and take time and sketch this off yourself and see what you can come up with. We're going to sketch a vector that is, the direction is 30 degrees west of north. And then name it differently is what they want in B. So when you get back, we'll do them together. Okay, I'm going to assume that you've stopped the video and you've done this, and we're going to take a look at it now. So it's a sketch a vector that has a direction 30 degrees north of west. So we can start off right here. I'm just going to draw a line down and a line across. Okay, there's my compass. Here's north, here's east, oops, kind of east, here's south, and here's west, right? So they want us to draw a vector that has a direction 30 degrees west of north. Well, here's north. To go west of or from the north is to go clockwise, right? We're going to go this way. So we're going to, and it wants 30 degrees. So I'm going to imagine 30 degrees right here. Here's 30 degrees. I'm drawing it. My vector's right there. 30 degrees. 30 degrees west of north. I'll highlight this a little more. How's that? So we're from north, we're going this way, 35 degrees west of north. Then it says, give a second description for the direction of this vector. Well, I kind of alluded to it in the previous slide. What could you do? You could say that this is, if this is 30, you know there's 90 degrees, right? You could say that it's how many degrees going the other direction from, we're headed from, here's where we're headed from to the vector. So we're headed from the west to the vector. So we are 60 degrees. In this case, we're 60 degrees north, because we're heading toward the north of west. So that's going to be 60 degrees north of west. Okay? You got it? Good. Okay, example 3. It's a real-world connection here. Example 3 shows how to describe a vector's magnitude and direction when you are given its description as an ordered pair. Here's our problem. An airplane lands 40 kilometers west and 25 kilometers south from where it took off. The trip can be described by the vector -40, -25. Use the distance for magnitude and direction to describe this vector as a second for a second way. Okay. To find the distance, use the distance formula. So how are we going to set up the distance formula? The distance formula says we're going to take the square root of the x, which is where we ended, minus the where we began. So that's going to be -40 minus 0. We started at 0 and we ended at -40 kilometers. You look over here on the chart, you see where we started at 0 and the vector went down here, but where for the x, we ended up going out to here, -40. Then for the y part, it's plus -25 minus 0 squared. So the y part going down in y is down here to -25. From here down is -25. You see it right here, -25. So you add those together. So -40 minus 0 squared plus -25 minus 0 squared is equal to the square root of 1600. That's -40 squared plus 625, which is 25 squared. And that gives you 2225, which, so the distance is the square root of 2225. Okay, and that's going to be in kilometers. And so when you take that square root, you're going to see that it's the distance is approximately equal to 47.169905. You'll use your calculator to get that value. Then once you have that, you can find the direction of the flight. Find the angle of the vector south of west. So we know we're going south of west because we started and went in a counterclockwise direction from the horizontal east-west line. Okay, so we take the tangent of x. We want to find, we're trying to find x, right? So the tangent of x is equal to what? It's equal to 25. So here's our angle. It's the side opposite, -25, divided by the side adjacent, -40. So when you divide that, they become positive. But anyways, tangent of x is equal to 25 divided by 40. And when we solve this by using the inverse, right here, inverse the -1, the inverse tangent of 25 divided by 40, you're going to approximately get 32.005383. So Do they say they want us to solve? Let's see. They're not saying that they want to. They don't care how we describe it in terms of. No, no, we're good. So we don't have to estimate anything. So it says the airplane flew about. The about word is because it's an estimate, right? It's an estimate right here because we did this tangent, inverse tangent. 47 kilometers at 32 degrees. So 32 is what we calculated is our angle, and its angle is south of west. So here it is. This x right here then is 32 degrees, and the distance is 47 kilometers. So that's our vector described as a distance and a direction. Okay, example 3, check your understanding. So a small plane lands at a point 246 miles east and 76 miles north of a point from where it took off. Describe the magnitude and direction of its flight vector. Okay, so they want you to do this, so I'll give you some time. Why don't you go and stop the video, take as much time as you want. Work this problem out. When you come back, we'll work it together. Okay, so now that you've had time, I took the time to solve the problem too. So let's see. A small plane lands at a point 246 miles east and 76 miles north of a point from where it took off. Describe the magnitude and direction of its flight vector. Well, to find the distance it flew, that's the magnitude they're looking for, we're going to use the distance formula. And the distance formula says that the distance is equal to the square root of the x minus x1 minus x0 or x2 minus x1, okay, squared, plus the, what is it? It's the y2 minus y1 squared. So it's 246 minus 0 squared plus 76 minus 0 squared. And when you take and you bring when you do the math on that, you're going to get 60,516, which is the square of 246, and 5,776, which is the square of 76. And when you add those together, you're going to get this. Take the square root of 349,500. Let's see. Let's put some commas. It's 3,449,540,416. Taking the square root of that, you're going to get approximately 257.472328 miles. That's the distance. Okay. To find the angle, we're going to take and use the tangent. Since we have the x distance and the y distance, and we know that x over y is the tangent, so the tangent of x, the angle we're looking for, is equal to 76 divided by 246. Well, to solve for x, we need to take the inverse tangent. So x then is equal to the inverse tangent, or the tan inverse, right here, tan inverse, of 76 divided by 246. And when you take that tan inverse, you're going to get 17.168172 degrees. That's the angle we're going to get from the inverse tan of 76 divided by 246. So that means that the plane landed at a point 257 miles at 70 degrees north of east. So what does that look like? It looks like what? We have a calendar like this, a compass like this, and we're north of east, so we're going out somewhere in this direction, and it's going to be very low, but it's going to be 17 degrees is the angle, and the length of this is going to be 257 is going to be the length of this vector. So, and I think that's really, in proportion, it's going to like really go way, way, way out, right? With a small angle. But that's just a quick little drawing to get to see the picture. The 17 degree angle, which is right here, which is bigger, it's more like 45 degrees, but you get the picture. 17 degrees at 257 magnitude. Okay, continuing objective 2, or with objective 2 rather, adding vectors. You can also use a lowercase letter such as u, as we're showing here, vector u, to name a vector. This map here shows vectors representing a flight from Houston to Memphis. Okay, it started down here in the corner here at Houston, right here, and it ended up way up here at Memphis. Okay, so with a stopover in New Orleans. So that means it flew out and the vector u and went to New Orleans and then took off from there and vector v and went up to Memphis. Okay, the vector from Houston to Memphis is called the sum or the resultant of the other two vectors. You can write this as the vector w is equal to the vector u plus the vector v. So you can add vectors by adding their coordinates. You can also show the sum geometrically. So let's look at this. Adding vectors. For a equal x1 comma y1 and c, the vector c, equal x2 comma y2, then vector a plus vector c equals x1 plus x2 comma y1 comma y2. You just add them together and you'll get your new vector. Okay, objective 2b is the second slide here. It says adding vectors. A vector sum can show the result of vectors that occurred in sequence, such as in the airplane flight described previously. A vector sum can also show the result of vectors that act at the same time, such as when you row in a direction different from that of the current. See the diagram. So in the plane flight, the plane went to one city and then to the other. So those two vectors could add, and you ended up with the resultant. Okay, but in this case, they're talking about the vectors are adding simultaneously. You're heading in one direction, and there's another vector pushing you in a different direction. And that's what this vector here, this picture is showing us. So it shows a canoe traveling in the direction here. This is the direction that the canoe is traveling, right? It's in this red direction here, as the arrow is pointing. And it's hitting a current, and the current is pushing it in this direction. So what is the resultant? Well, you're paddling in the one direction, the current is pushing you in another direction, and where the direction is actually you're traveling is this third direction here, and I'll change the colors, I'll use yellow. It's this one here that goes along. This is the direction you're traveling right here because the current is pushing you away from the target you're aiming at. And so it ends up traveling in this direction at a different speed too, by the way. So, okay. Okay, example 4, adding vectors. Vectors A and C are shown in the diagram. Write the sum of the two as an ordered pair. Then draw vector E, the sum of A and C. So A plus C, vector A plus C is equal to the ordered pair 4, comma 3. That's of the one vector, and minus 1, comma 2 is the C vector, right? So now we want to add them. And in order to add them, we're going to add the x values and the y values. So the x values, there's 4 plus negative 1. Here's the 4, and here's the negative 1, the x values from these ordered pairs. And the y values are 3, right here, 3 and 2. Okay, so you add them separately. The x's add and the y's add, and you end up with 4 minus 1 is 3, and 3 plus 2 is 5. So your new ordered pair is x equal 3, y equal 5. Okay, so the resultant is 3, comma 5. That's our resultant vector. So it says draw A with its initial point at the origin. So A starts right down here with its initial point at the origin, okay? And then draw C with its initial point at the terminal point of A. Well, the terminal point of A is right up here at what? 4, comma 3. And we know it's 4, comma 3, right here. 4, comma 3. And then from there it says, finally draw the resultant, oh no, I'm sorry. Then draw C, the vector C, with its initial point at the terminal point of A. So the initial point of C is we're going to be right here at the, I'll change colors, right, oh, I don't want to use red. I use this blue. Right here, okay, now we've drawn the starting point of C, and where our ending point of C is up here at 3 and 5. Right up here, 3 and 5. So what is the final vector? The final, it says draw the resultant vector E from the origin down here, and I'll do that in green. E is down here at the origin. We're going to start it here, and the terminal point of C. So the terminal point of C is up here. So here's our vector going from the origin up to, see if I can draw it a little straight. I don't know. There. So that's our vector now. And that is, as you can see, it's goes from 0, the origin, out there to point 3, 5. Okay, example 4, check your understanding. So pause the video and go ahead and try this problem on your own. It says write the sum of two vectors, 2, 3 and -4, -2 as an ordered pair. Okay, go ahead and pause the video. When you come back, we'll do them together. Okay, I'm assuming you've done that. You're back. So let's look at it. So what do we have? Two vectors. Here's the first vector. Here's the second one. The x values are these two. And the y values that change color here. And the y values are these two. So let's start off by adding the x. So to add, you just add vectors, you add them, right? It's the sum. So the first one, we've got 2 is the first x, and it's plus -4. Okay, and then that's the one vector. And the other one is we're adding these, right? So then it's 3 and -2, right? That's comma 3 plus -2. So this is now our ordered pair, x and y. Okay, so when you add these together, over the y over here, these should have been red, sorry. This is going to be a 1. And then I'll do the green here. This is going to be 2 minus 4 is -2. And it's a comma there. And I'll use, not red, I'll use yellow. How's that? This is our ordered pair. It's -2, 1. Okay, example 5. It's a real world problem here. A ferry shuttles people from one side of a river to the other. The speed of the ferry is still in still water is 25 miles per hour. The river flows directly south at 7 miles per hour. If the ferry heads directly west, what are the ferry's resultant speed and direction? Okay, the diagram shows the sum of the two vectors. To find the ferry's resultant speed, use the Pythagorean theorem. So you see that we're going, the speed is 25 miles due west. We have a current that's heading due south at 7 miles per hour. And we want to find x and c, the angle at which we're traveling from the west, and the speed, which is c. So in order to find the vector, the speed, c, we're going to take and use Pythagorean theorem, which is c squared is equal to a squared plus b squared, right? Or 25 squared plus 7 squared. We have our 7 and our 25. Those are our two legs of this right triangle opposite the hypotenuse, which is c, and we're looking for c. So c squared, then, if you multiply those up or square those values and add them, you're going to get c squared is equal to 674. And 674, right here, 674, the square root of 674 and c, taken both sides, c is approximately 25.96. Okay, that is the distance, or the magnitude. Okay, excuse me, not distance, the speed. Okay, so instead of going 25 miles per hour, we're going 25.96, almost 26 miles per hour. Then says to find the resultant direction, we use trigonometry. And what is it? We're going to use the tangent. We have both legs. We don't have the hypotenuse. So whenever that's the case, and the angle we're looking for is across from the opposite, the 7 miles per hour. So that's going to be our opposite, and the 25 will be our adjacent, or the x over y, or the 7 over 25. So the tan of x is equal to 7 divided by 25. But we need the inverse tan because we want the angle. We know what the tangent of the angle is, but we don't know what the angle is. So what is the angle? So x, the angle, is equal to the inverse tangent of 7 divided by 25. And when you do that inverse tangent, you're going to get x is approximately equal to 15.642246. That's using your calculator. So the answer to the problem then is the ferry speed is about 26 miles an hour. Its direction is about 16 degrees south of the west that it's heading. Okay, and you can see it right there. C is south, heading is south of west. Okay? Okay, now it's your turn. Check your understanding. Use the diagram to find the angle which the ferry must head upriver in order to travel directly across the river. Take your time and work it out. Okay, so now that you've had time to work this problem, let's take a look at it. So use the diagram to find the angle at which the ferry must head upriver in order to travel directly across the river. Okay, so to find the angle, we're going to look at what do we have? We're looking for an angle, and the angle is right here, x, down here. All right, here's the hypotenuse going off. Here's the right angle. Right here's the right angle. So you know that this is the hypotenuse. It's the angle across the leg across from the right angle. And this angle x here must mean that 7 is opposite. Okay, x down here, the blue line is adjacent. We want the 7. So we're using the opposite and the hypotenuse to come up with this angle. And opposite over hypotenuse is sine. So to find the angle, we take the sine of x, and that equals 7 divided by 25. The opposite divided by the hypotenuse. And then that's what we're looking, that's what the equation is, but we want to find x. We don't know x. So they're giving us what the sine of x is. We want to now take the sine, what it is, and figure out what the angle is. So you have to solve for x. So x equals the inverse, right here, inverse sine of 7 over 25. And the inverse sine of 7 over 25 is approximately equal to 16.26024, 0204. So that means what? That means that the ferry must travel upstream at an angle of approximately 16 degrees if it wants to meet its endpoint right here directly across the river. Because as it's traveling upstream here at this angle, the stream is constantly leveling it out and pushing it down lower and lower and lower till finally it ends up hitting right here.